Okay, I'm going to do a little modelling on here of an exam question which does some of these things and maybe puts it into a bit of context for you. So on your worksheet, hopefully you've done something similar to the first question, but I'm still going to do this. So it says, first of all, explain how a line emission spectrum leads to an understanding of the existence of discrete electron energy levels in atoms. So I'm noticing it's 3 marks there, so I need to have 3 points, of course. So let us begin. So first of all, if it's an emission spectrum, then I'm asking myself where the coloured lines have come from, as opposed to the dark lines like your worksheet. So in this case, then I can say that each line represents a photon of light, or a discrete value of a photon of light emitted. Each photon then has a discrete value for energy, since they have specific wavelength or specific frequency. This implies, so that's mark number 2, there are discrete energy levels for the electrons in the atom. Just worth reminding ourselves here that these emission spectrum, they only happen in gases. Emission spectrum is in a hot gas, the absorption spectrum is in a cold gas. So I'm just reminding you of that. So here we go. This is an emission spectrum. So this is one of the ones I can see. There's no colours on it, so I have to notice that it's horizontal and it's got a wavelength like that. So this is a real spectrum. That's what I'm being told. And it's telling me the wavelengths of each one. So the photon energies associated with some of these lines are shown. It says complete figure 7.2 by calculating the photon energy for a wavelength of 486 nanometers. So here I have to remember E equals HF, or E equals HC over lambda, because V equals F lambda. So I'm just rearranging, and V, remember, is the speed of light, because this is electromagnetic radiation. So now I can just rearrange that to find the, well, I don't have to rearrange it, I can just substitute. So E equals Planck's constant, 6.63 times 10 to the minus 34, multiplied by the speed of light, 3.0 times 10 to the 8, divided by the wavelength that I've been given. I've got to be careful, it's got a prefix, 486 times 10 to the minus 9. So let us find out what that is. So we've got, I'll use 2 brackets to be sure, multiplied by 3 times 10 to the 8, close brackets. I don't really think I need all these brackets, but it doesn't matter. I'm just making sure I get it right, really. 486 times 10 to the minus 9, close, equals, and then I've got a value that is got a 10 to the minus 19 on it, and I can see my rounding is 4.09 times 10 to the minus 19 joules. Just checking that I've got that at the end, 4.09. There we go. So that's the first part of this question done. Okay, do we have it on the back? No, it's on another sheet. Let's get another sheet. So this is just something similar to the ones that you are doing. Here we go. Here's the next part of that question. Now what I'm looking at is an energy level diagram. So this isn't something that I can see with my eyes. It's just something that I know represents the energy levels. So I'm noticing that that is in joules, so I don't have to do any conversion to electron volts. You may have to, so you have to look out for that. So it says energy levels of a single electron and hydrogen are shown. There are quite a few lines there. Use data to show on figure 7.3 the transitions associated with each of the 4 spectral lines shown in figure 7.1. So this is figure 7.1, and it's asking me which energy changes have produced these photon energies. So it's actually fairly easy because it's just I'm looking for the correct numbers when I subtract one from another. So that's quite an easy thing to do as long as you know what that is. Now, if I look at these values and I look at these values here, all of these values are roughly 5 or just a little less than 5. And I'm looking at this ground state here, and that's a big difference between 21.8 and 5.45. So I know that none of the arrows are here. So I'm just going to play around with the numbers really, and I'm going to play around with them looking at that value. It's got to be relating to these because each of these numbers is around 4 or just under 4. The only way is if they're going to here. So I'm literally going to get to each one and just take them away and see what they are. So if I do 5.45 to 2.42, let's just literally subtract them. That gives me 3.03. Sure enough, on my chart there is 3.03. So that very first one must be 656. So I can now go, that dropping to there is 656 nanometers. Let's look at some of the other ones. I think I'm just going to do them one by one. So let's have a look. 5.45 minus 1.36 equals, there we go, 4.09. I'm looking on the chart. 4.09 is the one I just did. It's 486. So I'm going from there to there. That's 486 nanometers. So I'm labeling them with the wavelengths. So we'll go this one to the next one. 5.45 minus 0.87 equals 4.58. 4.58, is it there? Yes, it's there, so it's 434. So that is that one. And I can guarantee the last one must be that, mustn't it? It must be. So 458 is 434 nanometers. So let's see. Then the last one, I'm guessing, has to be that one. That has to be 410 nanometers. So that is it. That's my 2 marks. It's probably 2 marks for each one or something like that. And that is it. Okay, you could probably have a go now at the exam questions that are like that. Best of luck.